Hi students, in this video we are going to look at some special discrete distributions that comes up a lot in practice. First we are going to look at something called discrete uniform distribution. Let me show you the situation where it occurs. Consider a random experiment of picking a number from 1 to n at random. Let x denote the number that we pick. So x can take the any value from 1 to n. So x will be a discrete random variable with a support sx equal to 1 to so on n. Okay, let's look at the PMF function. The PMF function px of y, which is the probability of x equal to I, it should be 1 by n for I equal to 1 to n. Because x should take the any value from 1 to n with equal probability as we pick number at random. Fine. Okay, let's check the validity of this PMF. It should satisfy two conditions. One is it should be positive over the support and the total PMF values over the support must add up to 1. Let's see one by one. First of all, as we can see, the Px of y value 1 by n, which is a positive for 1 to n, and the total PMF values over the support 1 by n plus 1 by n plus 1 by n times, it add up to obviously 1. Okay, the valid PMF. Here x is said to have discrete uniform distribution over 1 to n. Fine. We have a notation for this. Okay, this is a notation. We read it as x follows uniform distribution over 1 to n. Fine. In assignment 3, we have seen this distribution and we computed expectation, variance and MGF, right? So, for this distribution, expectation of x is n plus 1 by 2 and the variance of x is n square minus 1 by 12 and MGF, mx of t is for t non-zero, e power t of e power nt minus 1 by n times e power t minus 1. For t equal 0, obviously it will be 1. Okay. This knowledge we have from assignment 3. Okay, fine. Let's look at an example here. Consider a random experiment where you pick a ball at random from the box containing 20 balls with the label 1 to 20. Okay, here x denotes the label of the ball we selected. So then x follows uniform distribution over 1 to 20. So here capital N equal to 20. Okay, so immediately we can see that the support of x going to be 1 to 20 and the PMF is 1 by 20 for all I equal to 1 to 20, and we can also say right away expectation of x going to be n plus 1 by 2, right? So 20 plus 1 by 2, which is 10.5, and the variance of x is n square minus 1 by 12, right? Here n equal to 20, so 20 square minus 1 by 12, which is 399 by 12. This is the variance. If you are interested in standard deviation, it's going to be square root of the variance. It's going to be 5.766. Fine. Once we recognize that x follows discrete uniform distribution, then we can use our knowledge about discrete uniform distribution directly. We don't have to compute everything from scratch every time they occur. Okay, fine. Next, degenerate distribution. Consider a random experiment where particular event E happens with probability 1. Here, define a random variable which quantify every outcome in E to some constant C. We can see that probability of x equal to C will be 1 because x take the value C whenever outcome come from E, and we know that E happens with probability 1. Here we don't mean that x doesn't take any other value. X may take some other values also, but with probability 0. X take the value C with probability 1. Here x is said to have degenerate distribution at C. Okay, so let's look at an example here. Consider a random experiment of picking a number from interval 0, 1. Here the sample space omega is interval 0, 1. Define a random variable which quantify every irrational number to 1 and every rational number to as it is same rational number. That is, x of omega is 1 if omega is irrational and omega if omega is rational. This is our random variable. So we can see that probability of x equal to 1 is probability of picking an irrational number which is 1. X take the value 1 if and only if the outcome is irrational number. We know that probability of picking an irrational number is 1. So here X is degenerate random variable at 1. Okay. So this is an example of a degenerate random variable. Okay. The discrete distribution that we are going to see next arises in experiments called Bernoulli experiments. Let's see what is the Bernoulli experiment. Bernoulli experiment, a random experiment in which outcomes can be classified as success failure type. Let me give an examples here. Tossing a coin. Head may be success, tail may be failure. Rolling a die, even success, odd failure. Picking a card from a deck, red card may be success, black may be failure. Picking an item from a lot, non-defective, success, defective may be failure. Appearing for a gate exam, qualified, success, disqualified, failure. Observing sex of a newborn child, boy, success, girl, failure. Sorry, let me change. Girl, success, boy, failure. Okay. A particular performance of a Bernoulli experiment is called Bernoulli trial. Okay, fine. Now we are going to see something called Bernoulli distribution. Bernoulli distribution. In a Bernoulli trial, we define a random variable which quantify success to 1, failure to 0. So x is a discrete random variable with support 0 and 1. Let p be the probability of success. Then we can write down PMF like this. Px of 1, which is the probability of x take the value 1. X take the value 1 only when we have a success. So the probability of success p. So Px of 1 value p. And Px of 0, the probability of x take the value 0. X take the value 0 only when we have a failure. So the probability of failure is going to be 1 minus p. So this is the PMF. We can easily verify the validity. So you can see that the PMF values are positive at 0 and 1 because Px of 0 is p and Px of 1 is 1 minus p. Both are positive, and both these PMF values add up to 1 because 1 minus p plus p equal to 1. So this is a valid probability mass function. Okay. Here x is said to have Bernoulli distribution with a parameter p, where p is the probability of success. Okay. Fine. Now we have a notation for this. This is the notation. We read it as x follows Bernoulli distribution with parameter p. Okay. Now we can look at expectation x to the power of k. For any k, it's going to be same p because expectation x to the power of k what? 0 to the power of k times px of 0 plus 1 to the power of k times px of 1. This is 0 and 1 times p. So this is going to be p for any k. All moments are going to be equal to probability of success for Bernoulli distribution. That is mu k dash equal to p for all k. Okay. Now, so in particular, expectation of x going to be p, and the variance of x, which is expectation x square minus expectation x whole square, p minus p square. So if you take p common, p times 1 minus p. So expectation x is p and variance of x is p times 1 minus p for Bernoulli distribution with parameter p. Okay. And we can also look at MGF. Mx of t is 1 minus p plus p power t, because what is the MGF? Expectation of e power tx, that is e power t times 0 px of 0 plus e power t times 1 px of 1. E power 0 is 1, so which is px of 0. So 1 times 1 minus p plus e power t, px of 1 is p. So we can write like 1 minus p plus p e power t, which makes sense for any t from minus infinity to infinity. Okay, this is the MGF for Bernoulli distribution. Fine. Next, we are going to look at generalization of the Bernoulli distribution, something called binomial distribution. Okay, binomial distribution. Consider a random experiment where we perform sequence of n independent and identical Bernoulli trials, each with a probability of success p. Here the sample space omega consisting of outcomes which are sequence of success failures of length n like this b1, b2, so on bn, where each bi is either success or failure for I equal to 1 to n. Okay, this is the sample space. Let Ek be the event consisting of outcomes in which we have exactly k success. Okay. Now we can see that number of elements in Ek will be n choose k. Already discussed this before in the previous classes. I'm not going to explain why this count is n choose k. And for every outcome in Ek, the probability of singleton omega going to be p power k 1 minus p to the power of n minus k for all omega belongs to Ek. The reason is every omega in Ek consisting of exactly k success n minus k failures, and we know the trials are independent. We also discussed these things before, so I'm not going to explain again these things. Okay, fine. Now let us define the random variable x, which denotes the number of success. X is a function from omega to r. X of omega is number of success in omega. So x is going to be discrete random variable which support 0, 1, 2, so on and. Now let's look at the PMF. The Px of k going to be probability of x taking the value k. X take the value k if and only if outcome coming from Ek. So the probability of Ek we can write the probability of singleton omega where omega running over Ek, and we know that for every omega belongs to Ek, the probability of omega is p power k 1 minus p power n minus k. So this one we can write summation p power k 1 minus p power n minus k, where summation varying over Ek. Okay. We are adding same thing p power k 1 minus p to the power of n minus k, number of elements in Ek times. So the number of elements in Ek times p power k 1 minus p power n minus k, and we already know the count for Ek, which is n choose k. So therefore PMF Px of k going to be n choose k p power k 1 minus p power n minus k for k equal to 0, 1 to so on n. Fine. Now let's check the validity of the PMF. Obviously, PMF values are positive for k equal to 0 to n. Now let's see if the sum of the PMF values or the support equal to 1. Okay, let's add up the PMF values or the support. Summation k equal to 0 to n Px of k, that is summation k equal to 0 to n choose k p power k 1 minus p power n minus k. Now we know from the binomial theorem, this is the expansion of p plus 1 minus p over to the power of n. Here p cancel, so 1 to the power of n means 1. So in fact, what we got is actually valid probability mass function. Fine. Here x is said to have binomial distribution with a parameter n and p. Okay. Here n is the number of trials in the experiment, p is the probability of success. Okay, fine. Here we have a notation. This is a notation. We read it as x follows binomial distribution with parameter n comma p. We have already seen this distribution earlier. In fact, we computed in the previous classes expectation of x is np, variance of x is np times 1 minus p. Okay. Now MGF going to be 1 minus p plus p power t equal to the power of n. Okay, it makes sense for any t between minus infinity to infinity. Easy. MGF is actually what? Expectation of e power tx is going to be summation k equal to 0 to n e power tk px of k summation k equal to 0 to n e power tk. The PMF what we got, n choose k p power k 1 minus p to the power of n minus k. Now this we can rewrite like summation k equal to 0 to n choose k p e power t power k 1 minus p to the power of n minus k. Okay. Again, using the binomial theorem, we can write p power t plus 1 minus p all to the power of n. Okay. That's why this is going to be MGF 1 minus p plus p power t all to the power of n, which makes sense for any t from minus infinity to infinity. Okay, this is the MGF. Fine. Now, here is the exercise. If x follows binomial distribution with a parameter n comma p, show that mean equal to np, variance equal to np times 1 minus p through MGF. This is a hint, okay? This is how you compute mean and variance through MGF. Fine? Next. Okay, problem. An airline knows that 5% of people who makes reservation do not turn up for the flight. So it sells 52 tickets for a 50-seat flight. What is the probability that every passenger who turn up for the flight will get a seat? We are going to compute this probability using binomial distribution. Okay, here each passenger either turn up for the flight, which we are going to call success, or do not turn up for the flight, which we are going to call failure. Here we know that 5% of the people do not turn up for the flight. That means 95% of the people do turn up for the flight. So the probability of success P going to be 0.95. Okay, here checking out these 52 passengers is like a performing sequence of 52 independent and identical binary trials, each with a probability of success 0.95. Okay, here let x denote the number of passengers who turn up for the flight. That means x is what? Number of success. The next follows binomial distribution with the parameter 52, 0.95. That is n equal to 52, p equal to 0.95. Okay, fine. Let A be the event that every passenger who turn up will get a seat. A happen if and only if x less than or equal to 50. Okay, so the probability of A going to be probability of x less than or equal to 50. This probability of x less than or equal to 50 we can write 1 minus probability of x bigger than 50. This probability of x bigger than 50 we can write probability of x equal to 51 plus probability of x equal to 52. If I apply minus, so it's going to be 1 minus probability of x equal to 51 minus probability of x equal to 52. And we know the PMF for the binomial distribution. Probability of x equal to k is what? N choose k p power k 1 minus p to the power of n minus k. Here n equal to 52, p equal to 0.95. Okay, now let us compute this thing. So if I use the binomial PMF, then this whole thing gets simplified to 0.74. So the probability of A, that is probability of every passenger who turn up will get a seat, is approximately 0.74. Fine. Okay, next. Next problem. It is known that the screws produced by a certain company will be defective with probability 0.01 independently of each other. The company sells the screws in a packages of 10 and offers a money back guarantee that at most one of 10 screws is defective. What proportion of the packages sold must the company replace? Again, we are going to answer this problem using binomial distribution. Solution. Here each of the 10 screws in a package is either defective, which we are going to call success, or non-defective, which we are going to call failure. Okay. Here the probability of the defective is 0.01. So the probability of success P is 0.01. Examining the package is kind of like a performing 10 independent identical Bernoulli trials, each with a probability of success P equal to 0.01. Okay. Let X denote the number of defective screws in a package. That is, X is what? Number of success in 10 independent identical Bernoulli trials, each with a probability of success 0.01. So, X follows binomial distribution with a parameter 10 comma 0.01. That is, N is 10, P is 0.01. Okay. So the binomial PMF probability of X equal to K is 10 choose K, 0.01 to the power of K, 1 minus 0.01 to the power of 10 minus K. Right? Fine. For K equal to 0, 1 to so on 10. Okay. Let A be the event that random package that is sold coming back to the company for replacement. A happen if and only if X bigger than 1. That is, number of defective screws in a package bigger than 1. Because company offers money back guarantee saying that that package contains at most one defective screw. Right? If it has more than one defective screw, you can send for replacement, right? So A happen if and only if X bigger than 1. So the probability of A going to be probability of X bigger than 1. This we can write 1 minus probability of X less than or equal to 1. So X less than or equal to 1 means X can be either 0 or 1. So it's going to be 1 minus probability of X equal to 0 minus probability of X equal to 1. Now using binomial PMF, we can write this probability of X equal to 0 this and probability of X equal to 1 this. Okay. So this whole thing gets simplified to 0.004. So only 0.4% of the packages sold coming back to the company for replacement. Okay. Fine. So the answer is only 0.4% of the packages sold coming back to the company for replacement. Fine. Okay. Next. The theorem n is large and p is small, but np is of moderate size, that is np equal to lambda. Then this binomial PMF n choose k p to the power of k 1 minus p to the power of n minus k will be approximately equal to e power minus lambda to the power of k by k factorial for k equal to 0, 1, 2, 3, so on. That is, if limit of np equal to lambda as n go to infinity, p go to 0, then the limit of binomial PMF n choose k p to the power of k 1 minus p to the power of n minus k equal to e power minus lambda to the power of k by k factorial as n go to infinity. Okay, we have to prove this. So what is given here? N is large and p small and np equal to lambda. That implies p equal to lambda by n. With this relation, as n go to infinity, obviously p go to 0. Fine. Let us start with the binomial PMF here, which is n choose k p to the power of k 1 minus p to the power of n minus k. N choose k nothing but npk by k factorial. Okay. This npk we can write n into n minus 1, n minus 2, so on, n minus k plus 1 by k factorial. Here we are replacing p with a lambda by n, so lambda by n to the power of k, 1 minus lambda by n to the power of n minus k. This we can write 1 minus lambda by n to the power of n by 1 minus lambda by n to the power of k. This is nothing but lambda to the power of k by n to the power of k. The next step, we can write this n to the power of k under this product. Okay, we can group lambda to the power of k, k factorial like this. Okay, n into n, k k times. So we can see like n by n, n minus 1 by n minus 2 by n, so on, n minus k plus 1 by n minus k plus 1 nothing but n minus of k minus 1 actually. Okay. So so if I, so that means n by n going to be 1, n minus 1 by n going to be 1 minus 1 by n minus 2 by n going to be 1 minus 2 by n, so on, n minus of k minus 1 by n going to be 1 minus of k minus 1 by n, like this. Okay. So let me write in the next step. So this binomial PMF is going to be lambda to the power of k by k factorial. So n by n is going to be 1, n minus 1 by n going to be 1 minus 1 by n minus 2 by n going to be 1 minus 2 by n, so on, n minus of k minus 1 by n going to be 1 minus of k minus 1 by n. So this is as it is. Now let us take the limit both sides as n go to infinity. Now as n go to infinity, we know that this 1 by n, 2 by n is all k minus 1 by n, everything approaches 0. Also this 1 minus lambda by n to the power of k approaches 1 minus 0 to the power of k. You should know one limit here. Limit n tends to infinity, 1 plus x by n to the power of n actually equal to e power x. Okay. So that means as n go to infinity, this will approaches e power minus lambda. So we can see this. Okay. So that's why finally the limit of the right hand side is going to be e power minus lambda, lambda to the power of k by k factorial. So the limit of the binomial PMF n choose k p to the power of k 1 minus p to the power of n minus k is going to be e power minus lambda, lambda to the power of k by k factorial as n go to infinity for k equal to 0, 1, 2, 3, so on. Fine. Okay. Let me clear this. Now we are going to look at another discrete distribution called negative binomial distribution. Consider a random experiment where we perform sequence of independent identical Bernoulli trials with a probability of success p until rth success is obtained. Here the sample space omega consisting of outcomes which are sequence of success failures like this, b1, b2, so on, bn, where n is the number of trials that we are using to see the rth success. Okay. So there are exactly r of the bs equal to s, and we always end with rth success, so bn must be equal to s. So bs are either success or failures. So n must be greater than or equal to r. So to see r success, we need at least r trials, right? That's why n must be greater than or equal to r. This is how outcomes look in the sample space. Now let Ek be the event which consisting of outcomes in the sample space which having exactly k failures. We already know outcomes in the sample space having exactly r success. Now outcomes in omega also having exactly k failures. So any outcome in Ek must have r success and k failures. So must have a length k plus r. So they look like this: b1, b2, b3, so on, bk plus r minus 1, bk plus r. Okay, and they always end with the rth success, right? So this must be success. So from b1 to bk plus r minus 1, there must be exactly r minus 1 success. Okay, so remaining k are failures. Okay, so that's why the number of elements in Ek must be equal to k plus r minus 1, choose r minus 1. Now for any omega in Ek, the probability of singleton omega going to be p power r 1 minus p power k, because for every outcome in Ek having exactly r success and k failures, and trials are independent, so we can see this. Fine. Now let's define a random variable x which denotes the number of failures before the rth success. So x is a function from omega to r. Here each outcome is quantified to the number of failures in the omega. That is x actually what? Number of failures before the ortho success. Okay. So now let's find the PMF of x. Px of k equal to probability of x equal to k. X take the value k if and only if outcome coming from event ek, because only outcomes in ek having exactly k failures, right? So probability of x equal to k going to be probability of ek. The probability of ek we can write probability of singleton omega, where omega running over ek. And we know that for every omega belongs to ek, the probability of singleton omega is actually p power r 1 minus p power k. Okay, so therefore, so we are adding p power r 1 minus p power k number of elements in ek times. So that's why this is going to be equal to number of elements in ek times p power r 1 minus p power k, and we already realized that the number of elements in ek is going to be k plus r minus 1 choose r minus 1. So therefore the PMF Px of k is what? K plus r minus 1 choose r minus 1 p power r 1 minus p power k for k equal to 0, 1, 2, 3, so on. Okay, this is the PMF of the random variable x. Okay, fine. We can also express the same PMF in terms of the extended binomial coefficient like this. Okay, actually what is our PMF here? Px of k equal to k plus r minus 1 choose r minus 1 p power r 1 minus p power k for k equal to 0, 1, 2, 3, so on. Okay, now we can actually express this ordinary binomial coefficient k plus r minus 1 choose r minus 1 in terms of extended binomial coefficient, where the top parameter is negative integer like this. We have a relationship between extended binomial coefficient minus r choose k and the ordinary binomial coefficient k plus r minus 1 choose k like this. Minus r choose k actually equal to minus 1 to the power of k, k plus r minus 1 choose k. Okay, here minus r is a negative integer. Okay, so this is going to be extended binomial coefficient, and k plus r minus 1 choose k going to be ordinary binomial coefficient. This is a relation we have between extended binomial coefficient and ordinary binomial coefficient when the top parameter of extended binomial coefficient is negative integer. Okay, fine. Now this k plus r minus 1 choose k, we can actually write k plus r minus 1 choose r minus 1, because we know we have identity that n choose r always equal to n choose n minus r. From that we can easily say that k plus r minus 1 choose k same as k plus r minus 1 choose r minus 1. Now in our PMF, this ordinary binomial coefficient can be replaced with this involving negative binomial coefficient. When the top parameter of extended binomial coefficient is negative integer, we can also call it negative binomial coefficient. Hence the name here, negative binomial distribution. Fine. So this is going to be our PMF. Px of k going to be minus 1 to the power of k minus r choose k p power r 1 minus p to the power of k for k equal to 0, 1, 2, 3, so on. Okay. Now let us check the validity of the PMF. Okay. First condition, the PMF values are positive over the support, because we can immediately see that this is positive for all k equal to 0, 1, 2, 3, so on. Now let us see if the sum of the PMF values over the support add up to 1. If I add up all these PMF values from 0 to infinity, so let's use this one. Okay, the Px of k is what? Minus 1 to the power of k minus r choose k p power r 1 minus p power k. So if you write this p power r outside, then p power r times the summation k equal to 0 to infinity minus 1 to the power of k minus r choose k 1 minus p to the power of k. This summation can be realized as expansion of 1 minus of 1 minus p all to the power of minus r, because we should know when u is real number, the extended binomial theorem says that 1 minus x whole to the power of u expansion going to be summation k equal to 0 to infinity minus 1 to the power of k, you choose k, x to the power of k. Okay, this is the expansion of 1 minus x whole to the power of u. Here, the role of x played by 1 minus p and the role of u played by minus r. So that's why this summation we can write 1 minus of 1 minus p whole to the power of minus r. Here 1 cancel. So it's going to be p power r times p power minus r. So it's going to be 1. Fine. So this is a valid PMF. Okay. Here x is said to have negative binomial distribution with a parameter r, p, where r is the number of success need to achieve, p the probability of success. Okay. We have a notation here. This is notation. We read it as x follows negative binomial distribution with a parameter r comma p. Okay. We have already worked with this PMF in assignment 3. We got expectation of x r times 1 minus p by p, variance of x r times 1 minus p by p square. We also got MGF, which is p by 1 minus of 1 minus p e power t whole to the power of r, which makes sense in this interval. Fine? Okay. Now, exercise. For the negative binomial distribution with parameter r comma p, show that mean equal to r times 1 minus p by p, variance equal to r times 1 minus p by p squared through MGF. Okay, you know how to compute mean and variance through MGF. Fine. Okay, next. If we are interested in y, which is the number of trials required to the rth success, then y can be expressed in terms of x like this. Y equal to x plus r, because number of trials required to see the rth success is going to be number of failures before the rth success plus r, right? And obviously y will take the value r, r plus 1, r plus 2, so on, because to see r success we need at least r trials. Okay, fine. Now let us write down the PMF of y in terms of PMF of x. Okay, PMF Py of y equal to probability of y equal to y. Here y equal to x plus r, right? So y take the value y if and only if x take the value y minus r. Now we can use the PMF of x. What is the PMF of x? The probability of x equal to k is what? K plus r minus 1, choose r minus 1, p power r, 1 minus p power k. Now the role of k played by y minus r. So let's simply replace k with a y minus r here. So y minus r plus r minus 1, choose r minus 1, p power r, 1 minus p all to the power of y minus r. Here r cancel. So we end up with a PMF Py of y equal to y minus 1, choose r minus 1, p power r, 1 minus p power y minus r for y belongs to S5. Okay. Now we can easily see expectation of y in terms of expectation of x like this. Expectation of y, that is expectation of x plus r, as y equal to x plus r. Okay, and expectation of x plus r, we can write expectation of x plus r, because we know that expectation of ax plus b going to be what? A times expectation x plus b. Here a equal to 1, b equal to r. That's why you can write expectation x plus r, and we already know expectation of x, which is r times 1 minus p by p. So this whole thing gets simplified to r by p. So therefore expectation of y going to be r by p. Similarly, the variance of y, that is variance of x plus r, going to be same as variance of x. The reason is variance of ax plus b actually equal to a square times variance of x. Okay, here a equal to 1, b equal to r, so it's simply like a 1 square variance of x, 1 square anyway 1. So variance of y going to be same as variance of x, which is r times 1 minus p by p square. Okay. In the same way, we can also find MGF of y in terms of MGF of x. Okay, mgf of y, my of t, we can write like this: p power tr mxt. The reason is this: mgf of x plus b at t, we can actually write e power tb times mgf of x at at. Okay, so here a equal to 1, b equal to r, because y is what? X plus r, right? So here a equal to 1, b equal to r. That's why mgf of y at t, we can write e power tr mx t. Fine. Now we already know mgf of x. Let's use it here. So e power tr p by 1 minus of 1 minus p e power t all to the power of r. This we can write p e power t by 1 minus of 1 minus p e power t all to the power of r, which makes sense in this interval. So this is going to be mgf of y. Okay, where y is number of trials required to see the rth success. Fine. Okay. Next is the problem. Suppose you are surveying people exiting from a polling booth and asking them if they voted independent. It is estimated that the probability that a person voted independent is 0.2. Question 1. What is the probability that 15 people say no before you find 5 people who voted independent? Question 2. What is the probability that 12 people must be asked before you find 6 people who voted independent? Okay. We are going to answer these probabilities using negative binomial distribution. Here, asking people if they voted independent is like a performing Bernoulli experiment, because they may say yes or no. Yes, success, no, failure. Okay. Let X denote the number of people who say no before you find 5 people who say yes. That is, X is what? Number of failures before the 5th success. So X follows negative binomial distribution with a parameter 5 comma 0.2. Here R equal to 5, the probability of success P, which is given 0.2. Okay. Here in question 1, we are interested in probability of x equal to 15. That is, probability that 15 people say no before you find 5 people who say yes. Okay. So here we can use the negative binomial PMF to compute the probability of x equal to 15. What is the PMF of the negative binomial distribution? The probability of x equal to k is k plus r minus 1 choose r minus 1 p power r 1 minus p power k. Here r equal to 5, p equal to 0.2 and k equal to 15. Now we can compute probability of x equal to 15 using negative binomial PMF. Okay, the probability of x equal to 15, 15 plus 5 minus 1 choose 5 minus 1, 0.2 to the power of 5, 1 minus 0.2 all to the power of 15. This will be simplified to values which is approximately 0.0436. This is the probability of x equal to 15. Fine. Next question. What is the probability that 12 people must be asked before you find 6 people who voted independent? That means here number of trials. We should be interested in number of trials before the 6th success, right? Let y denote the number of people must be asked before you find 6 people who voted independent. So y actually represent number of trials required to see the 6th success. So here we are interested in probability of y equal to 12. Okay, the probability of 12 people must be asked before you find 6 people who voted independent. Fine. Here r equal to 6, p equal to 0.2. Here we know that PMF of y is going to be probability of y equal to y is what? Y minus 1 choose r minus 1, p power r 1 minus p power y minus r. Okay, here the small y is going to be equal to 12. Okay, now let us compute the probability of y equal to 12 using this PMF. So probability of y equal to 12 is going to be 12 minus 1, choose 6 minus 1, 0.2 to the power of 6, 1 minus 0.2 to the power of 12 minus 6. This will be simplified to the value which is approximately 0.00775. Fine. So this is how we can use the negative binomial distributions answer problems like this. Okay. So fine. Next. Banach matchbox problem. A pipe smoking mathematician carries at all times two matchboxes. Each time he needs a match, he will take it from left pocket with a probability p and from the right pocket with a probability 1 minus p. Consider the moment when mathematician first discovers that one of his matchbox is empty. If it is assumed that both matchboxes initially contain capital N matches, what is the probability that there are exactly k matches in the other box for k equal to 0, 1, 2, so on, capital N? Okay. Okay. Here, going for a match is like a performing a Bernoulli experiment. The choice of left pocket we may see as success, choice of right pocket we may see as failure. The probability of success is going to be here P. Let Lk be the event that discovering left box empty and right box contain exactly k matches for k equal to 0, 1 to so on, capital N. Here, Lk happens if and only if n minus k failures before the n plus 1 success. Here, the mathematician discovers that left box empty when he go for left pocket n plus 1th time. At that moment, we want right box to have exactly k matches. That happens only if mathematician had gone to the right pocket n minus k times before he go for left pocket n plus 1th time. Okay? Because if he had gone to the right pocket n minus k times, that means he must have used n minus k matches from right pocket. So he will be left with exactly k matches in the right box. That's fine. Okay. So Lk happens if and only if n minus k failures before the n plus 1 success. Let x be the random variable, which is the number of failures before the n plus 1 success. Okay, then x follows negative binomial distribution with a parameter n plus 1 comma p. Here r equal to n plus 1 and p the probability of success. Okay, then the probability of Lk going to be probability of x equal to n minus k, because Lk happens if and only if n minus k failures before the n plus 1 success, right? That's why probability of Lk equal to probability of x equal to n minus k. Now we can use the negative binomial PMF, that is probability of x equal to k is what? K plus r minus 1, choose r minus 1, p power r 1 minus p power k. Here the role of k played by n minus k, role of r played by n plus 1, and p is p. So now using the PMF of the negative binomial distribution, we can write n minus k plus n plus 1 minus 1, choose n plus 1 minus 1. Here 1 1 cancel, 1 1 cancel, and p power n plus 1, 1 minus p power n minus k. Okay, this is r, this is like a k. So this is going to be 2n minus k, choose n, p power n plus 1, 1 minus p power n minus k. This is the probability of Lk. Okay, fine. Similarly, let Rk be the event that discovering right box empty and left box contain exactly k matches for k equal to 0, 1, 2, so on n. Similarly, we can argue that probability of Rk will be equal to 2n minus k, choose n, 1 minus p to the power of n plus 1, p to the power of n minus k. Okay. Now let AK be the event that there are exactly k matches in one box when other box found empty. for k equal to 0, 1, 2, so on n. Here AK happens if and only if exactly one of LK or RK happen. Okay, so AK is going to be LK union RK and both cannot happen simultaneously here. So probability of AK going to be, by finite additivity I can write probability of LK plus probability of RK. Therefore probability of AK going to be, this is probability of LK, this is probability of RK. Now if you take the 2n minus k, choose n common, so you'll end up with this expression. Okay, the probability of AK going to be 2n minus k, choose n, p power n plus 1, 1 minus p power n minus k plus 1 minus p to the power of n plus 1, p to the power of n minus k for k equal to 0 to n. So this is the probability of AK. That is probability of finding one box empty and other box contain exactly k matches. Okay, fine. Next. Now we are going to look at another discrete distribution called geometric distribution, which is actually special case of negative binomial distribution. Okay. In a sequence of independent and identical Bernoulli trials, each with a probability of success p, let x denote the number of failures before the first success. So x follows negative binomial distribution with a parameter 1 comma p, that is here r equal to 1. So x can take the value 0, 1, 2, 3, so on. Fine. Now let's write down the PMF of x as a PMF of the negative binomial distribution for r equal to 1. So immediately we can write down PMF of x, Px of k going to be k plus 1 minus 1, choose 1 minus 1, that is something, choose 0 means this is 1, p power 1, 1 minus p to the power of k, that is this whole thing gets simplified to 1 minus p to the power of k times p for k equal to 0, 1, 2, 3, so on. Here x is said to have geometric distribution with a parameter p. Fine. We have a notation here. This is a notation for geometric distribution. We read it as x follows geometric distribution with a parameter p. Okay. Now, as a negative binomial random variable, we can immediately answer expectation of x, variance of x, and MGF like this. Expectation of x is going to be 1 minus p by p because we know r equal to 1, right? Actually, r times 1 minus p by p, we are using r equal to 1. So, expectation of x is going to be 1 minus p by p. And the variance of x is going to be 1 minus p by p square because r equal to 1, right? So, actually, for negative binomial random variable, the variance of x is r times 1 minus p by p square. Here our r is 1. And we can also write down MGF of the negative binomial random variable with a parameter 1 comma p, just like this. Okay, simply we are using r equal to 1. This is the MGF of x, which is a geometric random variable now. Okay. Again, now if we are interested in y, which is the number of trials required to see the first success, then y going to be x plus 1. So y can take the value from 1, 2, 3, so on. Here r equal to 1. Again, we can write down the PMF of y. Y minus 1, choose 1 minus 1. Here r equal to 1, right? Something, choose 0, which is going to be 1. P times 1 minus p power y minus 1. Here r equal to 1. Okay. So therefore, the PMF of y, Py of y going to be 1 minus p to the power of y minus 1 times p for y equal to 1, 2, 3, so on. Also, we can answer expectation of y 1 by p. Actually, it should be r by p, but r equal to 1. Variance of y is going to be r times 1 minus p by p square, right? Again, r equal to 1. So, 1 minus p by p square. And MGF of y also we can write. We already know MGF of y, which is p power t by 1 minus of 1 minus p power t power r. Here we are keeping r equal to 1. So this is going to be MGF of y. Fine. Okay. The reason we are looking at this particular special case of the negative binomial distribution because this special case have a special property, something called memoryless property. And the geometric distribution is the only discrete distribution having this memoryless property. Okay, fine. Now let us see what is the memoryless property. Okay, theorem. If x follows geometric distribution with a parameter p, then for any two non-negative integers m and n, probability of x bigger than m plus n given that x bigger than m equal to probability of x bigger than or equal to n. First let me prove it, then I will explain what it means. Okay. Proof. Here x follows geometric distribution with a parameter p. So the PMF function is this. Px of k equal to 1 minus p all to the power of k times p for k equal to 0, 1, 2, 3, so on. Okay. Now let us compute probability of x bigger than I. To compute probability of x bigger than I, we simply add up PMF values from I plus 1 onwards. So summation k equal to I plus 1 to infinity px of k. Here the px of k is what? 1 minus p all to the power of k times p. So in this summation, terms are this. The first term is 1 minus p to the power of I plus 1 times p, 1 minus p to the power of I plus 2 times p, 1 minus p to the power of I plus 3 times p, and so on. So if you take p times 1 minus p to the power of I plus 1 common, then you will have 1 plus 1 minus p plus 1 minus p square plus 1 minus p cube, and so on. This is actually geometric series whose sum is going to be 1 by 1 minus of 1 minus p. So after taking this p times 1 minus p to the power of I plus 1 common, we end up with some geometric series whose sum will be this. Okay, so 1 by 1 minus of 1 minus p, here 1 cancel, minus minus plus, this p cancel, so we will be left with 1 minus p to the power of I plus 1. Therefore, probability of x bigger than I equal to 1 minus p to the power of I plus 1. Let's remember this. We will be using this result in future problems. Okay, fine. Next. Now let's prove this. Okay. Now probability of x bigger than m plus n given that x bigger than m, we know the conditional probability. Probability of a given b means what? By definition, probability of a intersection b by probability of b. A intersection b means a and b here, right? So this is like a, this is like a b. So the probability of a given b going to be probability of a intersection b. Here comma means end. So the probability of x bigger than m plus n and x bigger than m by probability of x bigger than m, but here x bigger than m plus n is kind of a subset of x bigger than m, because whenever x is bigger than m plus n, obviously x is bigger than m. So the probability of numerator going to be simply probability of x bigger than m plus n. The denominator is as it is. Now we know how to compute the probability of x bigger than m plus n. It's going to be 1 minus p to the power of m plus n plus 1, because probability of x bigger than I, we got 1 minus p to the power of I plus 1, right? So here I equal to m plus n, so the numerator going to be 1 minus p to the power of m plus n plus 1. The denominator probability of x bigger than m going to be 1 minus p to the power of m plus n. So it's going to be simplified to 1 minus p to the power of n. So 1 minus p to the power of n we can realize as 1 minus p to the power of n minus 1 plus 1. so that we can write this one as probability of x bigger than n minus 1. Okay, so probability of x bigger than n minus 1 we can also write like this, because x bigger than n minus 1 means x actually greater than or equal to n. So we got it. Okay, the probability of x bigger than m plus n, given that x bigger than m equal to probability of x bigger than or equal to n. This is something called memoryless property. The reason it is called memoryless property because the information that it has no success in first M trial is forgotten in subsequent calculation. That's why it is called memoryless property. Let's say you want to toss a coin until you see head. Let's say head is success, tail is failure. Let capital X denote the number of tails before the first head. The next follows geometric distribution with a parameter probability of head, right? Let's say you have not seen head in the first 5 trials. Okay, so if you are interested in what is the probability you won't see head in the next 3 trials also, that is the probability of x bigger than 8 given that x already bigger than 5. It's going to be same as probability of x bigger than or equal to 3, because this 8 we can see as 5 plus 3. Okay, so here the information that you have not seen yet in the first 5 trials is forgotten in this calculation. That's why it is called memoryless property. Okay, intuitively also it should make sense. Think about it. Okay, fine. Let me. Next we are going to show that the geometric distribution is the only discrete distribution having this memoryless property. Okay, next theorem. Theorem, let x be a non-negative integer valued random variable satisfying probability of x bigger than m plus 1 given that x bigger than m equal to probability of x bigger than or equal to 1. For any integer m, then x must follow geometric distribution. What is given actually? Memoryless property for n equal to 1. What is the memoryless property we mentioned? For any integer m and n, the probability of x bigger than m plus n given that x bigger than m actually equal to probability of x bigger than or equal to n. What is given actually for n equal to 1? That is enough to show x follows geometric distribution. To show x follows geometric distribution, we must show that the PMF of x must be in this form. 1 minus p to the power of k times p for some p. Okay, okay, let PMF of x is, let's say, px of k equal to pk. Next we have to show the pk must be in this form for some p. Okay, now let's name this probability of x bigger than m as a qm. Qm equal to what? Probability of x bigger than m. We can write this one in terms of the PMF pk like this. Summation k equal to m plus 1 to infinity pk. This is what? Probability of x bigger than m. Okay. Then in terms of these qm's, the probability of x greater than or equal to 1 means probability of x bigger than 0. In terms of this notation, it must be q0. So the probability of x bigger than or equal to 1 is going to be what? Q0 in terms of this qm. Fine. Now it is given that probability of x bigger than m plus 1 given x bigger than m equal to probability of x bigger than or equal to 1. Now using the conditional probability, we can write probability of x bigger than m plus 1 comma x bigger than m by probability of x bigger than m. Okay, the right hand side is probability of x bigger than or equal to 1. Now whenever x bigger than m plus 1, x also bigger than m, so this numerator probability we can simply write probability of x bigger than m plus 1, the denominator same, probability of x bigger than m, and probability of x bigger than or equal to 1 in terms of this qm's we can write q naught. Now again this one we can write qm plus 1, this one we can write qm. So we end up with a recurrence relation. Qm plus 1 by Qm equal to Q naught means this is the recurrence relation we got. Qm plus 1 equal to Qm times Q naught. Okay, fine. Now the Qm again we can write Qm minus 1 times Q naught. Again Qm minus 1, again we can write Qm minus 2 Q naught into again Q naught. So this is going to be Qm minus 2 Q naught square. If you repeatedly substitute, you will end up with a Q naught to the power of m plus 1. Qm going to be Q naught to the power of m plus 1. Fine. Now Q naught equal to probability of x bigger than 0, right? Probability of x bigger than 0 means you sum up PMF values from 1 to infinity. Okay, this we can write 1 minus P naught because the total PMF values P0, P1, P2, so on, everything going to be equal to 1. So this is going to be equal to what? 1 minus P naught. That's why the Q naught actually going to be equal to 1 minus P naught. Fine, because total PMF values must add up to 1. Okay, so Q naught, which is probability of x greater than or equal to 1, is going to be 1 minus P naught. Fine. Next, now Pk, which is a PMF value at k, that is probability of x equal to k, we can express like this. Probability of x bigger than k minus 1 minus probability of x bigger than k. Because x bigger than k minus 1 means x can be k plus 1, k plus 2, k plus 3, so on. From that, you are subtracting the possibility of x being k plus 1, k plus 2, k plus 3, so on. So only favorable thing is x must be equal to k. So that's why this event x equal to k we can actually express like this: x bigger than k minus 1 minus x bigger than k. Okay, so that's why the probability of this event, we can write probability of this event, and this is actually superset of this one. So that's why we can write this one, probability of x bigger than k minus 1 minus probability of x bigger than k. Okay, so now in terms of qm, this is going to be qk minus 1, this is going to be qk, and also we know that qm equal to q naught to the power of m plus 1. So in terms of q naught, this qk minus 1 we can write q naught to the power of k, this qk we can write q naught to the power of k plus 1. If you take q naught to the power of k common, then you will be left with this. So pk going to be equal to q naught to the power of k times 1 minus q naught, and also we know that q naught equal to 1 minus p naught. Okay, so that's why if you replace q naught with a 1 minus p naught, so we got this. So pk equal to 1 minus p naught to the power of k times p naught. So we got the PMF pk equal to 1 minus p naught to the power of k p naught, which is exactly PMF of the geometric distribution. So x must follow geometric distribution with a parameter p naught. Okay, p naught will be the probability of success. Fine. Okay, next example. A coin has been weighted so that it has 0.9 chance of landing on heads when flipped. What is the probability that the first time the coin lands on heads is after the 3 flips? Here, let x denote the number of tails before the first head. Here, head is success, tail is failure. So, x follows geometric distribution with a parameter p equal to 0.9. Here, the 0.9 is probability of head, that is the probability of success, right? Okay. Now, from the previous slide, we know that for the geometric distribution with a parameter p, probability of x bigger than k going to be 1 minus p to the power of k plus 1. Okay. Now, let A be the event that first time coin lands on heads is after 3 flips. So, A happens if and only if x bigger than 3. So, the probability of A going to be probability of x bigger than 3, which is 1 minus 0.9 to the power of 3 plus 1, that is 0.1 to the power of 4, that is 0.001. This is the answer. Okay. Fine. Okay. Let me stop now. Thank you.